I had a few people ask me about my binary encoding Lego activity. They were looking for a write-up. I don't have one, but I thought I had some time today to make a quick video. My school is closed because of the fires in Lawrence last night. So kind of see I have some Legos and some paper. The idea is that you want to build a tower, but you have to try to describe the instructions in binary. This is how everything we do is in a computer is modeled, right? You want to build an image. You have a bunch of ones and zeros. You have to find a way to describe the image into ones and zeros. You want text. You have to find a way to describe the text in ones and zeros. A come up with a set of rules on how to interpret the ones and zeros in order to display or create whatever it is that you're making. So we have a set of Legos. We want to find a way to describe how to build a tower out of them. We have to find a way to encode them. We have to create some rules. The rules, you can make up whatever you want. That's what I tell my students. You can make up anything you want. I can help by guiding them, but really sometimes they come up with some really good ideas. And I'll explain a couple of different variations of what you would do. You can start with Legos, and you can have like a blocks like these flat ones as like a design plane, or you can make just a little like XY grid for placing Legos. I make them about the size of one Lego, one little dot, so you can easily describe where to put them. So I think this is, I don't have enough of these usually to do this in class, so I usually just do this. I also use Duplo blocks sometimes because I think they're a little easier to manipulate for people than the tiny Legos. So I want to be able to say, put a block in this position at this level. I also want to be able to say which block. So I think it's easiest to kind of start with what block do I want to pick up. So I have to find a way to describe the blocks. Each block has a set of properties, and we can kind of build our descriptor of its uniqueness off that set of properties. So I think one of the first things you notice is color. So we can describe color. It helps help us pick which block. So if you want me to pick up a blue block, I know it has to be one of these. If you want me to pick up a red block, it has to be one of these. Besides that, you have to give a little more definition. Just blue is not enough. We have 1, 2, 3, 4 different kinds of blue blocks. So we have to find a way to describe the differences between those blue blocks. So what properties do we have that define them? I think the most obvious one is their size. The number of nubs is what I usually use in class. How many little bumps are on it? You can describe that in a couple different ways. You could say the width and the height. So you could say like the number this way and the number this way. You could say the total number of dots. It doesn't matter, just whatever the rules that you want to make are. And that's actually one of the big points of this exercise, is that there is no magic. Somebody or some group of people or some committee said, this is the way we map this thing to these ones and zeros. And that's how it happens. So you get to make up whatever you want. You're that committee. You get to say that we want to describe these by the number of nubs, width by height. Now you might just want to do the total number of nubs, but that can also cause some problems because you might have the same distribution of nubs in different shapes. Not typically, but it's possible. So another thing we want to do is define like which way the width is. And you can say, all blocks will be interpreted so that their width is the longest, the longest magnitude. So the biggest side is the width. So these are all organized with the width on the horizontal. So width and height. So we can say like this block is a 2 by 2. This block is a 2 by 1. This block is a 3 by 2. This block is a 4 by 2. Now that might not be enough. Now in the blues that's enough, but if you look at the reds, these two blocks have the same number of nubs and they're the same color. So we have to also define them by maybe their height. They're not their height in the two-dimensional plane, but this Z height here. So this is a double. I call this like a single and a double, or a flat and a big. So you have two different sizes there. So that's just some of the things we need to take into account. So how would you start to explain that? How would you start to model that? So the first thing I usually start this prior to doing this is we have just talked about how many bits does it take to represent something. How many bits does it take to represent 4 things? How many bits does it take to represent 10 things? So if you want to represent, one thing, if you have 1 bit, you can represent 2 things. If you have 2 bits, you can represent 4 things. If you have 3 bits, you can represent 8 things. And they usually pick up pretty quick that that this equation works of 2 to the number of bits equals the number of things you can represent. And what I mean by this is 4 has this many representations. The 2 bits has this many possible combinations of things we can pick. So let's pick, one of the things we can model here is like color. So how many bits do you need to model color? How many colors do we have to model? We have orange, red, green, yellow, blue, and white. So 1, 2, 3, 4, 5, 6. So we have 6 things. Well, we can't represent 6 things with 2 bytes because it's only 4 things. And we can represent 6 things with 8. Now that's not going to use up all those bytes, so we're going to have to decide what to do with that. Just some colors get 2 different explanations. Do we consider the other ones just garbage, what we call like a no-op, or just nothing? It's really up to the designer of the encoding. So we're going to say the first 3 bits of our instruction represent the color. And we can say that equals orange, equals red, equals green, equals yellow, equals blue, equals white. Now it doesn't matter what these numbers are. Yeah, like this is binary 5, but we don't care. It doesn't matter. It's the computer doesn't care. It's not using it as a number. It's using it to represent something else. So it doesn't really matter what these numbers are for binary. These are just the binary bits that represent these different colors. The rest of these, 1, 1, 0, and 1, 1, 1 are extras. We can decide whatever we want to do with them. We'll just call them no-ops. So, they don't do anything. If you get that in the instruction, it's an invalid instruction. That's an incorrect thing in the instruction. It doesn't have meaning. So that's 3 bits to represent color. Next, we want to say the number of width and height bumps. We really need to know what our largest ones here are. So our largest width is definitely this one, which is 1, 2, 3, 4, 5, 6, 7, 8. 8 things across. And this one's too high, and none of the other ones are bigger than too high. Yes, Legos exist that are not within these parameters, but you want to work with what's, this is what I tell them. This is the world. This is the all you have to worry about representing. The more Lego types you add, the more complicated this becomes. I'm not trying to make it really challenging. I'm just trying to get the point of all of this across. How does a computer do this? And the fact that it is just made up by people. And so this is our largest one we have here to worry about. And so this is 8 bits, 8 nubs across. And to represent that, I'm just going to use the binary number 8. So I'm going to 1, 0, 0, 0. I could actually map it from 0 to 7 because we don't have 0 size Legos. So 0 is 1, 1 is 2. But I'm just going to go with 8 meaning 8 and just 0 being non-representative of anything. And so it's going to take 4 bits to represent the width. And I only really don't need 4 bits to represent the width. I don't ever have a width here that's larger than 2. So I can actually, just use 2 bits. But I'm going to use 4 bits as well, just for consistency. It's just easier, I think, when you're trying to map it all out. But again, it's up to the creator. They can create it however they actually choose. So that means we're going to have 4 bits and 4 bits. I guess it doesn't really matter what they are, to represent the width and the height. So right now we actually have quite a bit of stuff to represent our Lego. We have our 3 bits for color, 4 bits for width, 4 bits for height. That's pretty good. That's going to get us through most of these Legos. But we actually also need to represent that thickness factor. And so I'm going to call this 0 and I'm going to call this 1. So this is a 0, this is a 1. And so we have to have one more bit as well. So 1 bit for thickness. And that's just going to be 1 equals, thick. And 0 equals thin. So what do we have here? So just to pick the Lego, I need 1, 2, 3, 4, 8, 12. So just to describe which Lego, I have 12 bits, and that's gonna pick a Lego. So you give me these 12-bit, and we can pick a Lego. Let's try one. Let's pick this balloon one. Now it's blue. If we go to our first chart, the first 3 bits are going to be that it's blue. So that's 1, 0, 0. So 1, 0, 0 is the blue. The next, we'll make it nice and computer friendly and say the next bit is going to be the thickness. And so this is a thick 1, so it's going to be a 1. And then its last 4 bits are going to be how high, width and height here. So 1, 2, 3, 4. So we're going to need to have a 4 and a 2. So I need 4 bits for each. Yeah, 2. So this bit string, this 12-bit string, represents this Lego. And it's actually, there's other Legos it represents. It represents any of these 3 Legos. Which is fine, because we don't need to distinguish in particular Legos, but it's certainly not any other Lego in this pile. No other Lego will yield this result. There are Legos that will be similar. This yellow Lego will have all of the same, except its color is different. So this is this blue one, and this yellow one would be yellow. Yellow is 0, 1, 1, 0, 1, 1. It's also thick. It also has the same size. So we have a unique encoding of a Lego. And I mean, frankly, you could stop here if you were really just trying to show just how you can encode something. But I like to take it a little further. And it's also a little more challenging. It also kind of is where most of the failure comes in. And I think failure is part of the fun in this because it's silly. The stuff doesn't build right. You choose the wrong colors, the wrong directions. So now we have to figure out how do you talk about placing these things down into a grid. So we have our 12-bit system. Actually, let me detail that first. This is our color, thickness, width, height. But that's not enough. That's not enough. How do you know where to put it? Now again, you have to establish some ground rules when we describe the width. We're talking about this. Whenever I talk about placement, I have to pick something. So I'm going to pick, whenever I talk about a location here, what I'm saying is that location corresponds to a corner on this brick. And now you could say, describe each of the four corners and where they lie in this system. So, you know, this one would be at 1, 1, this one would be at 1, 2, this one would be at 1, 5, this one would be at 2, 5. So it really just depends how you want to do it. Another way you could do it is to say this top corner is always the anchor point. So when I say 1, 1, what I mean is that top corner goes in 1, 1, or that top corner goes in 3, 2. And then you could specify also a rotation. So it's either, say, horizontal or vertical. So you could say that corner is at 3, 2, but it's vertically located. So it's up and down. So you have a number of ways you can actually just describe these two corners, and you'll always get the right orientation as well. So you can just describe a top right and a top left and lower right, or top right and lower left. It's whatever you want to come up with. So I like the corner and rotation method. I think it's less bits. It's easier to do. I think most students kind of do the multiple corners methods, 2 or 4. So I'm going to say that, what do I need to describe where I put one? Well, this square, unlike this, we could do the same thing with this. We just have to count the numbers here. This square right here, we'll say this has, just so it's nice and even, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7 by 7. In order to represent 0 through 7, I can use 3 bits. So I'm going to use 3 bits to describe the X and 3 bits to describe the Y of the top left corner. So we'll call this X and this Y. X, Y. Same way a computer screen is oriented. The axis of the top corner and positive Y going down and positive X going across. Then we need one more bit to decide orientation. Is it this way? Is it horizontal or is it vertical? And so one more bit for that. And that's for orientation. 0 equals horizontal, 1 equals vertical. So that's 3, 3, and 1. That's 7 more bits to describe where this is on the 2D plane. Now we have to decide one more thing. Are we explaining this one brick at a time, building a single brick on top of a single brick, oriented somehow, and so that every successive instruction is just the next layer? Or do we also want to describe what level it is on? I think either is fine. If you do what level it is on, you'll have to pick some limitation, and that's actually a pretty good discussion of just, it can't be infinitely tall because we have to pick some number of bits to represent it. So let's say we want it to be at least, at most 15 bricks tall, and we'll use a binary number to describe that, and then the location where our last bit will also be the Z. So let's do a Z bit, and we'll make that 4 bits. Should we make it 3 bits? I suppose we'll just make it 3 bits because everything else is 3 bits. It's going to limit us to 7, but again, you can yield that discussion of why what kind of trade-offs there are in limiting the number of bits to represent something. How accurately do you want to represent something? How much space do you want to use? How much data do you want to use to represent how much detail? We make those distinctions all the time. So let's try to build a tower and then explain it in our bits. Let me actually write out we have our picking the Lego, and now we have our locating the Lego. So let's say it's, let's just pick an easy one. We'll say we're going to describe this location right here for let's pick a, well, we don't have to worry about what color Lego it is. We'll just pick the location. So the top left corner is in 1, 1. So 3 bits in 1. It's got 3 bits 1. Oop, 1 too many zeros there. Let's do that again. 3 bits 1, 3 bits 1. And that's my 1, 1. My X here, my Z here, sorry, is, I suppose I'll do my orientation first. My orientation is next. It's horizontal, so it's a 0. And then 3 more bits for its Z. And this is at, say, we'll call this the 0 floor. And so that's our X. Or Y. I'm going to just call that OR for orientation. And our Z. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits. 10 bits. So it's going to take us at least, in our organization, it's going to take us a total of 22 bits. Now, you know, computers don't really do things in 22 bits, so maybe you pick 24 bits, and then you find some place to use that extra room. Maybe we put it in the Z's or the X's or the Y's. We find another place for it. Or we just leave it as 22, or whatever we want. I had a little camera issue. I lost some of the work I had done, so I'm going to kind of redo it. So let's just talk about how to make the whole 22-bit string now. So we have this 22-bit string. It's 3 bits for color. We have our color chart. 1 bit for thickness. We have a thickness chart. We have 4 bits for height, 4 bits for width. We have 3 bits for X, 3 bits for Y, 1 bit for 0, 3 bits for Z. And we just made this up, so we can do whatever we want. So now I'm going to encode just one Lego in one location, and it can be any location, any Lego. So let's just pick this orange one right here, and we'll put it at 3, 2, horizontal. Okay, so we know that the first things we need to do is 3 bits of color. Color orange is 0, 0, 0. Its thickness is the thicker one, and that was a 1. So 1, and then its width is 0, 1, 0, 0. Its height is 0, 0, 1, 0. Its X is going to be at 3 in 3 bits, so 0, 1, 1. Its Y is going to be at 2 in 3 bits, 0, 1, 0. Its orientation was 0, and its height is also 0 in 3 bits. So this would be the 22-bit string to talk about this Lego in this location. And we have a whole collection of these. You know, we have tons of bytes in a file, and this is a Lego tower file, a .ltf that I just made up. And when the computer sees a .ltf, it goes and does all of, uses this decoder here that we've created, and it creates what we need, interprets the 1s and 0s to create what we need from this set of rules that we've created. So I have actually a 5 tower one completed. This would be an LTF file. Now I have conveniently put each block on its own line, but in an actual computer, these would just all be in one big straight long line. I mean, the computer doesn't really have a distinction of row and height in the bit structure. It's just the file just has a collection in a row. So these would actually really be all strung together in one line, but just to make it a little easier, I put them in one line each way. So I got to figure out what this says and how to build this tower, and hopefully I get my own work right. So let's see. We know the first 3 bits are color, so this is color, and those 3 bits 0, 0, 1 are red. So we know that we need a red block. So right now we have red block. And then the next is its thickness. So we know it's not this one because it's a 1. Its next is its width and height. So its width is 4 bits, and that's a 4. That's it. Is it 4? 1 for thickness. All right, so here's our 4-bit, 4 bits. Here's our 4 bump one in the 4-bit. And then our height is 2. So we know it can't be this one, it has to be one of these. We don't need all of them, we just need one of them. And then our next is our location. So X, Y, Z. X is 0, 1, 0. So that's 2. And then our Y is, the next 3 bits is 1. So we'll put that at 2, 1. It's horizontal. And it's on the bottom. Okay, the next one, the next 3 bits are color. 0, 1, 0 is green. Its thickness is thick. It could have been either of these green ones, I suppose. Its thickness is thick. It's 4, so it's not that one. It's 2, it's the right one. Its location is 0, 0, 1, 0, 0, 1, so it's at 1, 1. And its orientation is horizontal. And it's above the one before it, red, so it's over here. Again, we have 3 bits for color. That's actually red, we know that. This is the thickness, it's a flat one. There's only one red flat one, so where is it? It's at 0, sorry, that's its width. That's its height. We already know those, though. We know this is the only one it can be because it's the flat one, so we can kind of just skip over those right now. As a human, a computer would obviously have to process them. And then its X is going to be at the same place the red one, so is its Y. It's also horizontal, and its Z is 3, so it's going to go like this on top of the green one. See it building. This next one, the 3 bits 0, 1, 1, our color. That color 0, 1, 1 is yellow, so it has to be one of these. Its thickness is 1. These are both 1, so that's, well, we have to continue. It is a 2 by 2, so it's this one, not that one. 2 by 2. And its location is at 2, 1. So it's actually at the same place as this red one. And we can see in the last little bit, it's right above it. With its orientation doesn't matter, so it doesn't matter if it's horizontal or vertical. And then 0, 1, 1, that's 4, so it's the 4th one up. The next one, 0, 0, 1, we should be getting used to that one. That's red. Well, 1 for thickness, so it's got to be one of these. It's a 2 by 2 piece. Its location, X, Y, Z, X, 3 bits. Y. So it's at 4, 1. So 4, 1. And yeah, it's on the same level as the previous one, so they're next to each other. And that would be the encoding to create this in this location right here. There's like a million variations on the encoding, and there's probably a million variations on how you actually do these. You could say you have to start with one square and then just describe what color goes next. You could make it a super simple tower, just what color goes next. It's tons of variations on what you could encode. So I hope that helps.